All right, so continuing on from Friday when we were dealing with momentum and impulse, now we're going to talk about collisions. All right, so let's just revisit impulse. So impulse was applying a force on an object for a certain period of time to cause there to be a change of momentum. So in order, if something's coming at you, to slow it down, you have to apply a force for a certain period of time, or if you want to speed it up as it's coming, you can apply a force for a certain period of time in order to change its momentum. So we would say the change in momentum, the mass times its change in speed, is equal to the force you put on it for however long it's acting. So force times time is defined as the impulse, and impulse is equal to your momentum change. So the theorem here, impulse momentum theorem, pretty much states that these guys are going to be equal to each other no matter what. And then we can use this equation to solve for, all right, the one piece of missing information. So if we know the change in velocity, the force in times, we can figure out the mass. If we know m and impulse, we can figure out the change in velocity. If we know m and delta v and the force, we can figure out how long. Those were part of the things that were on the homework for on Friday. So the most important factor in a collision is going to be the time. More specifically, the time it takes to come to rest. So this will reduce your chances of getting severely injured or dying in a car. So do we want to increase the time of impact, or do we want to decrease the time? Why increase?
Because the sooner they come out, the more survival you have chance.
Right, so if this is the equation, if this is my equation here. So, right, no, well, think about it. No matter what, you're moving at a certain speed and you have a certain mass. That's not changing, right? So let's say you're moving 30 miles an hour and you got to get down to 0. You're going to change your momentum by however much that is. Now, if you do so, you can do it basically in one of two ways. If you have a large force and a small time, when you multiply them together, okay, or a smaller force over a longer period of time. Which one would you rather? Option 1 or option 2? 2. Why? Because the force is less. So by increasing the time, we're going to overall decrease the force. They're inversely proportional here. And why does that? Well, I could stop quicker, which when you think about real quick, you're like, oh yeah, I'd rather definitely stop quicker. But when we break it actually down, right, that'd be like slamming into something hard, and that would wind up hurting a lot because it's going to apply a much larger force on us. So the airbags come out. The seatbelt is there. The seatbelt is designed to give just a tiny bit before it locks. Okay, that again increases your time before you come to a complete stop. Then you have the airbag that comes out. Your face goes down into the airbag. And what happens to the airbag? The airbag kind of caves in. What is that doing? It's increasing your time, which is going to wind up decreasing the overall force acting on us, which is what we want. Okay, that's why the front of cars are designed to crumple. So you can only be going like 10 miles an hour and bump into someone, okay, or 5 miles an hour, and they're going to actually look like more significant damage than you would think, because why? The cars are designed to kind of crumple in like that. All right. Again, the overall idea is so that they decrease the amount of force. You can get a new car, okay? You can't really get a new person, new life type of deal. All right. So that is why our impulse is used tremendously. It's used in all kinds of different sports: football, basketball, volleyball, hockey, golf. How would we use momentum in golf?
With the backswing going to hit the ball, when the ball is in the air, when it goes to land,
Yeah.
rolling of the ball when you're on the green.
So technically, when puck's in the air.
Puck's in the air, puck's on the ice. When you're moving, right? So like think about it. If you and who's the biggest kid on your team? Okay, so you and the big dude are going towards each other. If you're both going the same speed and run into each other, who's carrying the more momentum? He's got the more momentum. So if you two were colliding head on at the same speed, he's got more momentum, so your momentum is going to change more than his. Okay, we're going to take a look at that today. We're going to take a look at the differences in collision, and as far as golf, yeah, the driving, right? Obviously, we're swinging with a much larger velocity when we increase, because we're trying to increase the velocity as much as we possibly can, so we're using a much larger force. But when you're putting, you don't want to use a lot of force because you only want it to go a couple feet, so you're not using as much force because you don't want to change the speed that much. So there's all different ways that we can use momentum just in everyday life, or we do use it, but we don't necessarily always think about it. So now we're going to take a walk into collisions and what in the heck a conservation of momentum is. So an isolated system, dudes and ladies, is pretty much when we're just looking at one specific case. We're ignoring everything else that's outside of it. So a collision was basically something or two things that make contact with each other. Okay, now the isolated system, there's no other outside forces that we're going to pay attention to. We're ignoring them. They're not going to be involved in our problems, which is good. So the law of conservation of momentum is this. When no outside forces are acting on the system, okay, that is consisting of two objects that collide with each other, the total momentum before is going to equal the total momentum after the collision. Okay, regardless of who applies the larger force on the other. Okay, so let's take a look-see at. So when we say, okay, there's this thing, impulse and auto collisions. Okay, so in these collisions that we are going to deal with, the problems that we're going to break down, momentum is always going to be conserved. All right. Direction is important. So if we have something going to the left, we're going to give it a negative velocity. Something going to the right, we're going to give it a positive velocity. Now, the two types of collisions that we're going to work on are perfectly inelastic and perfectly elastic collisions. Most collisions in the real world are just inelastic, not perfectly. So what is that? It's when objects hit each other, something's going to deform. Okay, they can stick together or they can bounce off each other. Kinetic energy is not going to be conserved. So some of that energy is going to be converted into other types of things, such as heat, sound, or work that's used to permanently kind of like deform the object. So everyday collisions, most of them are inelastic. But we are going to deal with perfectly inelastic. So basically what that is saying is the momentum before they collide is going to equal the momentum after. So one side of the equation is going to equal the other. Okay, so how do I know? Well, if the objects collide and get stuck together, it's perfectly inelastic. And this is going to be the equation that we use. Now, it looks like it's a lot. If I said, hey, I have a ball that's moving, what is its momentum? P equals what? Mass times speed, or mass times velocity, right? Is that difficult? No. So that's literally the first thing. Okay, right there, mass times the first, all right, mass of the first object times its speed. So I have P1 is equal to P2, the mass and velocity of the second object. You add them together, you're going to get a number. That's got to equal what this side calculates out to be. So once they get stuck together, these two things are moving as like one whole piece. So what we would do is we would add their masses together and figure, okay, well now they're both going to be moving at the same speed. They're both going to be moving at the same speed. Why? Because they're stuck together. So we're going to take a look, all right, at something like that in a second. Okay, in this it kind of explains the momentum of the first object before and after, before this for the second one, afterwards. Here's an example problem. Here is an example problem. So you have an inelastic collision. You have a 1,250 kilogram car stopped at a traffic light. A 3,550 kilogram truck is moving at 8.33 meters per second. what is that in miles per hour? So let's say 8.33 times 2.24 about. It's not too fast. All right, it's moving around just about 18 miles per hour. Okay. But do you think that's going to do some moves, some damage? Probably, yeah. All right, so what happens is the truck hits the car from behind. Now, if the car and truck stick together, that's how I would know, okay, this is an inelastic collision. And if I want to know how fast will they be moving, all right, as this new cluster here. So I've found, guys, over my years of teaching that drawing out like a little diagram helps. And I write all the information. So here's the 1,350 kilogram, 550 kilogram truck, and it's moving to the right at 8.33 meters per second. So this is the before side. The car was not moving, so it has 0 meters per second. It has a certain mass. After they collide, right, they're stuck together. So you have this object and this object stuck together, and now they're moving at a new speed, this final speed. What I would always tell my students is after you get the drawing, write the equation underneath it, because then it's very, very easy. And you'll see right now. So if I wrote out the equation, M1 V1 is equal to M2 V2 plus, M1 V1 plus M2 V2 equals M1 plus M2 over VF. And you're like, all right, what is all the hell? I don't even know what all these things are. Relax. That's why I tell you to put it under the drawing. So the mass of the first object is right here, this 3,550. So it is going to go here under M1. And its velocity, okay, put it here. Simple. Velocity of the second object, V, that's 0. The mass of the second object is this 1,250. Plop it here. Equals, well, the mass of the first one didn't change, so it's still this 3,550, and the second one is 1,250. Multiply that, or you're going to add them together and multiply by VF. Okay. So then, once you can do that, now it's just simple. Now it's just multiplying and subtracting or dividing. Multiply them together, you're going to get this answer. You're going to get a value of 29,571.5. Anything times 0 is 0. And this is going to equal, okay, these two values added together, that comes out to be 4,800 even, times whatever the heck our new speed is. So the 0, we pretend like it's not there because that doesn't matter. And since this is 4,800 times VF, you divide both sides by that 4,800, and you would be left with your new speed, your final velocity. And that would be the truck and the car both moving together. And then you're going to look at elastic collisions. And we're going to say that when this happens, objects are going to bounce off each other. And both momentum and kinetic energy are going to be conserved. So in this case, here's an example of the beforehand. Mass of the first object and its speed, mass of the second object and its speed. So we have that right here. So this is the momentum beforehand. And this is going to equal the momentum after. So wait a minute, what the heck are these little tick marks here? So you'll see that on multiple different like sites or other resources, and they use the word prime, which is just basically saying this is a new velocity after they collided.
V1 prime.
Yeah, V1 prime, V2 prime, which is basically saying, okay, this is the speed of this object after the collision. This, V2 prime, is the speed after the collision. And that's it. So here's an example. You have two objects moving towards each other. In this case, you have a 3 kilogram object moving at 3 meters per second to the right, and a 2 kilogram object moving 2 meters per second to the left. That's before the collision. Afterwards, they tell you that the 2 kilogram ball bounced off and is going to the right at 4 meters per second, and the 3 kilogram object, okay, here we're showing it, already showed it going to the left, but you can just like sometimes you can work the whole thing out, and then if it comes out negative, you would know that it moved left. So sometimes we're not sure. If this is a large enough momentum, it can knock this thing going to the right, and this guy could still be moving to the right. So we write everything that we know after underneath our drawings. So this is the only thing we don't know. We don't know the speed, the new speed of the first object. So first step I would always tell everyone is to write out your equation for the elastic. M1v1 plus M2v2 is equal to M1v1 prime plus M2v2 prime. So you're basically going to be using one of two equations. And then after you write that underneath the drawing, look at how simple this becomes. You guys are just dropping the values down. So M1 was 3. Cool, I put it 3. V1 was 3. Simple. Bring down the plus sign. Mass of the second one happened to be 2 here. So this way, now since it's going left, you see the arrow going left, we would say that this is a negative 2. Okay, drop down the equal sign. The mass of the first guy didn't change, so it's still the 3. We don't know what this dude is, the V1 prime. So this is like what we're going to wind up being looking for. Whoop. And we have our other guys here, 2 and 4. From there, we're going to start to simplify. 3 times 3 is 9. 2 times a negative 2 is negative 4. 3 V1 prime, okay, that's basically just saying like 3x if we were looking at regular algebra. And 2 times 4 is 8. Okay, cool. Let's simplify this again. 9 plus a negative 4 is 5. We're still not doing anything with this, so we have 3 V1 prime plus 8. Now, I need to get 8 off this side. So since it's plus 8, we got to subtract 8 from both sides. And when we do, we're left with a negative 3 is equal to our 3 V1 prime. So to get this guy isolated by himself, you got to divide both sides by 3. And in this case, we left with a final answer here of negative 1 meters per second. So that would tell us this object would be moving to the left. That would tell us, okay, this thing is moving to the left. All right. So with all of that being said, the assignment that I posted for you guys, if you open those up, okay, we're going to start with the elastic collision one. So you're going to go into go to the classroom, open up this one, open it with Cami so we can edit the PDF. All right, gotcha, Jay. So in this very, very first one, did I not put that here? Dope. Okay. All right, so I gave you guys like directions in this, yes?
Yeah.
Okay, so in the directions,
We delete one of the PDFs. They're both the same thing.
no, they're not. They're different. One is for elastic and one is for inelastic. So we're going to look at the elastic one first. So what do I say here? Okay, in collision 1, the blue car is initially at rest, and the red one is going to be at 5 meters per second. Okay, so blue car, it doesn't show me the ability here, but I'm just going to say V equals 0 meters per second. And what did they say the red car was supposed to be?
5
5.
meters per second.
They already have the unit there for me on that one. Okay. So now, what was the mass of the red car? I said to set it to. Mass should be 1 for the red, and blue should be 3. So mass should be 1, and blue should be 3. So guys, now you have a lot of the information that we pretty much needed. So let's take a look at the red car. Now this whole column here is before the collision. This whole column here is before the collision. So what is the mass of the red car?
0. No, 5.
What? 1.
Oh.
Mass of the red car. Okay, what was the speed of it? 5. Okay, so now, what is 1 times 5?
5.
So that is the momentum of the first cart. 5 kg meters per second. I'm just going to copy that because I'm going to need that in a minute. You can, yeah. Blue car. What was the mass of that guy? 3. What was its speed, though?
0.
If something is not moving, what is its momentum?
0.
Simple. So when it says system total, you add, okay, the red and blue car.
So 5 times 3.
15.
15.
No, not. So you add the total, right? So here's the momentum for the red car is 5, right? And what is the momentum of the blue car? 0. So we're just going to do 5 plus 0, and that is going to give us 5 kilogram meters per second as our total momentum before collision. So based off the notes that we were just using, the momentum before the collision has to equal the momentum after, right? That's what we should wind up seeing. So now what we're going to do is we're going to set these pieces of information up. So I'm going to go into this one. Can you just make sure you read me the correct numbers here? The mass of the red is 1, right? And the speed is 5. Mass of the blue should have been 3, and
1 for red.
and it's 0 for the speeds. I'm pretty sure that's correct.
Yeah.
Okay, making sure I'm on elastic collisions. And now I'm going to run this. Okay, so they bounce off each other. So that was elastic, right? So if they don't stick together, that's elastic. Like they bend and they bounce off. Okay, inelastic, they're going to wind up sticking together. Okay, so the negative sign, like we said in the notes before this, is important. So now what we got to do is we're going to go into the mass of the red car. Did it change? No, the mass isn't going to change. Well, what is the speed of the red car now? Negative 2.5. Okay, so what's 1 times negative 2.5? So now our momentum, the momentum of the red car after the collision is 2.5, or I'm sorry, negative 2.5. What is the mass of the blue car? It was 3. Doesn't change. Okay, well, what was its new velocity? A positive 2.5. And hit me.
5.5. 2.5.
Times 3.
Oh, I did.
Should be 7.5. Okay. No worries. So we have a positive 7.5. All right. So the system total is the red plus the blue. Okay, so what was the red's momentum after collision? Negative 2.5 plus 7.5. And what is that going to equal? It is going to equal 5 kilogram meters per second. Okay, interesting. Okay, so let's figure out what the change in momentum was. So I'm going to write this. You guys please write this as well. You're going to do P for momentum. Up top here next to the little paint can, you're going to hit that X sub 2 button. So P, all right, after, hit it again, minus P subscript before. So, what was the momentum after the collision for the red car? It was negative 2.5. What was the momentum of the red car beforehand? So, and when we're doing the total change in momentum, we're going across. The system totals, we go straight down. So these ones, all right, this column over here, this guy and this guy, you're going across, and then the system total would be, we're going down the column. Subscript is up here, this little X sub 2 button next to the paint can. So the momentum after is going to equal the momentum, the change is momentum after minus the momentum before collision. So the momentum after for the red car was negative 2.5, and before the collision it was negative 5. What does that equal? Negative 7.5 kilogram meters per second. For the blue car, you're doing 7.5 was the momentum after minus the initial, which was 0. So that equals a positive 7.5 kilogram meters per second. And then the system total would be the red plus the blue. So we're going straight down. So negative 7.5 plus 7.5. And what does that equal? Good. 0. Okay. So there's going to be a conclusion question at the end of this, which is going to ask you to make a claim as to whether or not momentum is conserved or not conserved. And then give evidence for those. Refer to specific sets of values in each data table that serve as your credible evidence. Write a paragraph with sound reasoning to argue why the evidence logically led you to the claim that you're making. So your claim, guys, will be a combination of this. You found the momentum, all right, of both cars before the collision, and you added them together. You got the total. And that came out to be 5 kilogram meters per second, positive 5, right? After the collision, okay, yeah, they had new values, but when you still added them together, the total came out to be 5 kilogram meters per second. So the total value did not change, which means the momentum has to be conserved. Even though the red car changed its momentum, all right, it changed it by a negative, it decreased or it changed by a negative 7.5, and the blue car increased by 7.5. When you added those two together, there was still no net change in momentum. 0, which is why this value is still 5 and not 7, 6, okay, 4. It's the same number as 5. All right, so 5 beforehand, 5 afterhand. So that will be kind of basically your conclusion. Okay, now since I'm recording this, you can go back and watch it and use that to kind of help yourself. So now you guys are going to complete the second one. In this second one, what values does it say to use? Let's go back to the classwork. So for collision 2, make the red 2 kilograms and the blue 1. So red 2, blue 1. 2 kilograms, 1 kilogram. What would the velocity of the red one? I told you to make it 8 and blue 2. Because it tells us here, set the initial cart of the blue set the initial velocity of the blue cart to be less than the red, so that's why I picked 2 instead of, because it's less than 8. And okay, give the blue car a smaller mass. So the blue is 1 instead of the red being 2 kilograms. Okay. So you guys have the information needed. I would do this though. Under system total, I'd write red plus blue. And under change in momentum, I would go up and I would copy this thing. And I would paste it there. And then you can fill at least the before column in. So the red car should be 2 for the mass, the blue car should be 1, the red car speed should be 8, the blues should be 2. And you can multiply them together, get their momentum of the first one, momentum of the second one, add them together, and that's going to tell you what the momentum is before they collide. The red car will be, 8 times 2, and the blue will be 2 times 1. So then you got to run the simulation where the mass of the red is 2, the blue is 1, this and this. Now, you can click on the cars and move them along as well. This is still elastic, and then you're going to hit the start button. You see what happened? Let's move this to back here. Okay, so the new velocities of the blue is 10 and red is 4. And they're both positive because they're still both going to the right. Okay, you're going to take your masses, you plop them there, and then you're going to repeat the process as you did in part 1. And again, the conclusion will be kind of the same like I had said. So you can go back and watch if you didn't quite get all of it or you weren't paying attention. But again, let's just take a quick peek. So your conclusion should wind up being somewhere the fact that you calculated the total momentum of both objects before the collision. You got 5. You ran the simulation, you calculated the new momentums, and when you added them together, you got the total momentum as 5. Okay. Even though the first one changed its momentum and the second one changed its momentum, the overall net change in momentum was 0, which is why this answer here is 5, and therefore momentum is conserved.
So we're just doing the right columns. So it would be 8 plus 1.
Okay, so you guys will please finish that. Afterwards, I'm going to, now we're going to set you up on the inelastic collision one. So make sure you have that PDF open via Cami. So for the inelastic collision, before they collide, we're going to say that the mass of the red car is 2, and the mass of the blue is 3. So I'm going to go reset. Mass of red is 2, mass of blue is 3. What about the red speed? Red is 7, blue make it 0. Okay, and we got to switch it to inelastic. All right, so now going here, we said the red was 2 mass of blue was 3. Before the collision, the red was 7 and 0 for blue. I'm just going to write that in just because. Now, since they get stuck together, they're going to be both moving at the same speed. So let's pipe in our pieces of information here. You have 2, you have 7. Add those together, you're going to multiply them, you're going to get 14. Blue, you're going to do 3 times 0. Multiply them together, you get a total of 0. So the system total, still the same thing like before. Okay, blue plus red. So 14 plus 0. And that will equal 0 kilogram meters per second. Okay, so while you guys are writing that down, I'm going to write just the P after minus P before. Normally we would say final minus initial, but because they're using before and after here, that's what I decided to go with. And now you need to run the simulation to find out what their new velocity of these objects is going to be. So let's hit the start button. Okay, so see how they're both moving at 2.8? Well, yeah, that makes sense because they're stuck together. So they're both going to have the same new velocity. They're both going to have 2.8 here. The masses didn't change, so this is 2. This one was 3. And now we can multiply out. 2 times 2.8 comes out to be 5.6. And then 3 times 2.8 should become 8.4. And they're both positive because they're both going in the same direction here.
So then 5.6 plus 8.4.
So what? Tell me what I'm doing.
5.6 plus 8.4.
Good. 5.6 plus 8.4. What does that equal? 14 kilogram meters per second. Oh, somebody should have told me I made an error here. 14 plus 0 I put as 0.
14. Yeah,
It's 14. So again, what we're seeing is that the momentum before the collision is equal to the momentum after the collision. How is that possible? Well, think about it, right? If we look back at the simulation.
Is it because it's positive?
Well, they're both positive, right? So you see that the red one was moving fast, yeah? The red one's moving fast. This guy's not moving at all. So now that once they hit, now they've collided. So now their momentum, the total momentum before is going to equal the total momentum after. Because right here, what we're going to look at is there's going to be a change. This one's momentum decreased. Why? Because he lost speed. He didn't change his mass. He lost speed. But this one was going 0, and now it is moving. So this one gained momentum. So the momentum lost by one is going to equal the momentum gained by the other, which should still equal the original total. And that's what the math shows us here, right? So what was the momentum of the red car after? It was 5.6, yay? What was it beforehand? 14. So how much momentum did this thing lose? It lost 8.4 kilograms meters per second. Where over here, after the collision, the blue car has 8.4 kilogram meters per second, when before it had 0. So the red car lost 8.4, but the blue car gained 8.4. So when we add right here, right, so going down this row, when you go down the rows, you add the red and blue. So here's the change in momentum of the red car. Here's the change in momentum of the blue car. So the red was negative 8.4, and the blue was a positive 8.4. When we add those together, we get 0. So the net overall change is 0. Even though they individually changed, the combination of the two is 0, which is why we got 14 here as the after collision, which is the same as our 14 before the collision. Bless you. Yep, I don't know. So then I said, for the last collision, this is for inelastic collision 1, then run the new 2 cards combined. So you're going to basically do the second one the same way as we just did this first one. But I'll tell you what your values should be. Tell you what the values here should be. So let's make the mass of the red one 3 kilograms, because it says we got to make the red one, all right, bigger, and then the velocity of the blue car less. So let's make the red one 8 meters per second, the blue one 2. Mass of the red one, we'll make it 3. Mass of the blue, will make it 1. So 3, 1.
You just want us to delete everything?
You
just want us to delete everything?
No, there's 2 separate PDFs.
There's 2 separate PDFs. So if you scroll down, Joe, right? So here's the first one. If you keep scrolling down on the Inelastic, there's the second one. The first PDF was the elastic collision. This one. This second information, I set you up with, but now you're going to do the same. So now I'm on the inelastic side where they are stuck together. So this was our information for that first one. And this is going to be your starting information for the second one. So you're going to set this up on the simulation and run, but let's run it real quick together. So let's reset. Let's change this as inelastic. The mass of the blue, we should say, is 3. The mass of the blue is 1. This was originally at 8, and this one is originally at 2. And then start. So 6.5 is going to be the after collision velocity. So we have 6.5. So that means this dude here has got to be 6.5. This dude here has got to be 6.5. Masses didn't change. And then you're going to basically just repeat. So again, this may be helpful if you just kind of highlight this dude here and you bring it down. And then over here under system total, you write blue plus or red plus blue. Thank you.
So 8 plus 2.
What do you mean 8 plus 2?
For the before.
For this one?
8 plus 2.
Why are you doing 8 plus 2?
You have for the bottom. System total.
Well, you forgot to multiply them.
I already multiplied them.
Well, it's 3 times 8.
24.
Okay, so this one's 24, and what is this one?
2.
Okay, so then why were you saying this answer was 8?
I said 8 plus 2.
No, it's 24 plus 2. Because you're using the momentums here.
Oh, okay.
Okay, so 24 plus 2. And that will give us 26. I'm going to highlight this thing so I can use it again. kilogram meters per second. So when you multiply this, you get an answer. You multiply this, you get an answer. When you add those two things together, it should also become 26. What did you say it was?
6.5.
Times 3 was what? 19.5?
Yeah.
Okay, so this was 19.5, and then obviously 1 times this is... Okay, so then I'm going to add 19.5 plus 6.5, which equals 24. Sorry, I lied. 26. Okay, so the momentum after minus before. So 19.5 minus 24. What does that equal? Negative 4.5. Over here, if you hit the refresh, it should show. Whoop. All right.
That's it. Class over. Ready?
Yeah.
So happy birthday.
Okay, so guys, you are to make sure that you finish this. I will post this video later. Okay? If you were not fully paying attention, or you just need a quick refresher, you can watch that and sim through that. Okay? I'm just gonna finish this little piece off here real quick. So I had 6.5 was my after, and my initial was 2. So when I do that, I get a 4.5.
I can turn this right now instead of
Well, you got to do the conclusions.
I already did that.
Okay. So then red plus blue, negative 4.5. Whoop. Plus 4.5 equals 0.
Have a good day, Mr. Lombardi.
You too, bud. So the net change, guys, turns out to be the red car changed its momentum. It lost 4.5 kilograms times meters per second worth of momentum, where the blue car gained 4.5 kilogram meters per second worth of momentum. So the overall change in momentum for the whole system is 0, which makes sense because, right, the momentum beforehand, this 26, equals the momentum afterwards, this 26. Okay, so make sure you use that somewhere in your conclusion. Okay? All right. You guys, I will see you tomorrow. Please make sure that you have this completed and submitted.